I'm very happy to have another young Indian with us today. Right now, we have with us Anshuman Acharya. Let's listen to him. Over to you, Anshuman.
Yeah. Uh, can we just start the screen recording, please? That's
You want to share the screen? Okay,
sharing
hang
the
on.
screen. Yeah.
Let me just
Yeah.
pause the recording while I do that.
Yeah.
Okay, we are back from the pause. Anshuman has set up his slide presentation. Let's see it. Let's go ahead, Anshuman. Tell us.
Yeah. So hello, thank you for this amazing opportunity to get to talk to you and talk about things that I'm interested in and what I've been doing. So I'm Anshuman. I'm a final year PhD student at the Max Planck Institute for Astrophysics in Germany. And I did my bachelor's and master's in India before coming to Germany, and I thought it would be nice to basically talk about what kind of a journey I've had, what kind of a journey that I've seen people around me take, so that students who are interested in this kind of path have a picture of what exactly lies ahead of them and what can they do about it. So it basically boils down to how to become an astrophysicist. Like you're an Indian student, from there to the international level, to the world. So, a good way to start would be to talk about what an astrophysicist does, because often even this is not somewhat clear if you talk to people randomly. Words like astronomer and astrophysicist are often used, and people get confused what is going on. But honestly, they are in the modern era, they are mostly interchangeable. They basically arose from two classes of approaches that this field took. One was for observations, which is the equivalent of what other sciences have in terms of experimenting. And that has kind of blended together, but it mostly relies on using telescopes to look at things up in the sky. So we try to think about what kind of physics we want to study, what would that look like if we look into the sky, and what kind of devices do we need, and how do they need to function in order to be able to record those behaviors. So then we can proceed to build those kind of telescopes, observe with them, and then compare it with what we already know in terms of existing theories and see if we can actually explain what we are seeing or if we cannot explain what we are seeing. And things get interesting when we cannot. The other part of it is being a theorist. And here is where you focus more on building models to explain the observations that could not be explained earlier with whatever we knew before. We also could then build a model and say that, okay, I have this model in place. Now, this is what you could actually see if you look at things from the telescope to test whether this model is right or not. So we can also pose questions for future observations. For all of these nowadays, theorists also use computer simulations. So often you'd hear theoretical astrophysicists introduce themselves as computational astrophysicists in the modern world. And these people are mostly employed in universities, research institutes, or observatories. On the other hand, what an astrophysicist does not do is basically being involved in the development of space technology. For example, that is the forte of ISRO, NASA, or other space institutions around the world. NASA actually is somewhat exceptional. They do have separate institutions where they employ astrophysicists, but their role is more for building instruments and calibrating them, checking if everything works fine in terms of the science goals that those instruments have to achieve in space-based telescopes. And overall, if you look at the astronomers and astrophysicists in the United States, only a small fraction are employed in NASA. And of course, on a lighter note, astrophysicists are not related to going up in space directly themselves. They're happy to just send their telescopes up there. They're happy staying on Earth and not venture up themselves. Now, becoming an astrophysicist, like how am I in this role now?
Okay, before you go there, Anshuman,
Yeah.
I know very little, but let me just ask based on that. Okay.
Yes, sure,
The
sure.
people who predicted Neptune and Pluto's existence, they
Yeah,
were astrophysicists, right?
sure. Yes.
Yes. They were not observers because they told the observers it must be there, so you better
Yeah,
check it. That's
yeah, yeah.
but and then who decided? that Pluto is a planet and is now not a planet?
Yeah, that's a very interesting question. Basically, it's so the International Astronomical Union was trying to define how do what a planet exactly means, because there are a lot of different these objects, even like asteroids that we have,
Yeah,
which are orbiting the sun, which
yeah,
have mass, which are uh, basically everything that a planet has, just smaller. They're just not spherical. So
yeah.
what the International Astronomical Union did was they defined that a planet is something that should also be able to clear its orbit. So if it has an orbit, it should not intersect with the orbit of any other thing.
Okay.
What happens is that Pluto's orbit is quite wonky,
Yeah,
and it has not really cleared its space. Its
yeah.
moon Charon is almost like a pretty significant fraction of its size. So it's very comparable in size to its moon, and it also intersects with the orbit of like I think um, Neptune a bit, and that's why it's not really a planet in terms of that definition. So does it mean that it's not a planet? No. People say that, okay, maybe we'll not call it a planet, we'll call it a dwarf planet. It's
Yeah.
not cleared its path, it still has a very big moon. Let's move, just call it a dwarf planet, and the rest are just planets.
Okay.
But yeah, that's about it. It's just a matter of definition, rather, which like all the International Astronomical Union had like all astronomers deliberate on it, and they were like, okay, fine, this is how it is. But yes, the first person who proposed this definition is like still a working professor. So he is quite famous in the field as the one who killed the status of Pluto being a planet.
Yeah. Yeah, I love this concept of Chota planet. I said,
Yes, yes,
I
indeed.
said, now we've got ourselves real scientists here. I mean, what do I know about science? But I thought it was quite funny that they first thought it's a planet, then they think it's not a planet. It's there, everything is known about it. It's just a
Yeah,
question of the name, you know.
indeed, indeed. It's just a matter of definition in
Yeah,
the
but a
end.
lot of school books have to be rewritten. Are there nine
Yeah,
planets or eight planets? We grew up with nine, but now they've gone down to eight. Okay, fine.
yeah.
Thank you. Let me not interrupt too
No
much.
worries. No, that's a fun question to have. That's
Yeah.
definitely very cool.
Okay, so let's continue.
Yeah. So I was talking about like what I've been doing, like how did I end up here? So as I mentioned, I did my bachelor's and master's in India in this institute called IISER Mohali. I had a bachelor's and master's in physics, and among most undergrad universities in India, this was somewhat exceptional, and our batch was the first to actually have this, and that was to have the option to have a minor in astronomy. So that we had enough courses, so now we could do that, and that was great. The basic idea that IISERs had was that they would take a very few students. In my time, they used a scholarship by the Department of Science and Technology of India, which was called KVPY. Now that's no more there, but now they use their own competitive exam and take students via that. And this course structure is somewhat modeled in terms of a merger between uh, course models in different places. So they take a core inspiration from the American system. So you don't really declare your major in the beginning. You have 2 years of physics, chemistry, mathematics, biology. They have a more natural sciences focus, but that's why they focus so much on these four subjects. But apart from that, they also have these interdisciplinary courses where they focus on, let's say, topics in engineering and things like that, and also some courses in humanities and social sciences, because the idea is that the first 2 years the student should have a well-rounded approach, and then they can pick and choose what they find interesting and declare one of the natural sciences as their major. So then in the beginning of the third year, I chose physics as a major, where we had also specialized electives, including a lot of them in astronomy. And of course, we still had to do a couple of humanities and social sciences courses, because again, the uh, picture that they had while setting this up was that even while you're doing sciences as a in natural sciences, you should still have a touch of what exactly you work, like what is the other side of the equation, what is happening in, say, sociology, what is happening in, say, urban planning, things like that. And the final year was mostly devoted to working on a master's thesis project. So you could just uh, do your research and then see how exactly does it feel to have worked some semi independently, in the sense that while you are still working under supervisor, you would be progressing based on what you can do, what is interesting to you, and things like that. And a cool thing that they promoted was that in every summer break, they would say, urge students that you should go out and try to look for internships, especially in research, so that you actually get a flavor of what exactly is it that the professors in IISER Mohali as well as other places actually do. Like, what exactly do they study in natural sciences? So in my case, the first year summer that I had in 2017, I went to the Tata Institute for Fundamental Research in Mumbai, and I looked at this field because it was pretty random. I had just entered physics and I heard this thing called condensed matter physics, and I did not know what that meant. So I was like, why not just do something about it? And turns out they basically talk about just different kinds of weird materials. So the lab that I was interested went to was interested to understand how do things which are solids but kind of behave like liquids, say like sand or something, or say a pile of any kind of particles, say pieces of glass or whatever, behave in terms of friction, which by that time, like as a student, I was like, who cares about friction? We know that it's okay, it exists, but why are they so interested? And it turns out that there are a lot of things that we still don't understand, and they were exploring that and looking how things behave at the small scale. So that was interesting. But I was kind of interested in astronomy. So the next summer, I went to University of California in Santa Barbara. So there I was finally able to get into computational astrophysics, something that I was always like, okay, this is something I've thought about as a kid, that it seems very interesting. Let's see what it looks like. And I worked on this project where we would look at like we'll take a galaxy and we would see, okay, if the galaxy is suspended in gas clouds, then what are those what are the properties of the gas clouds, and how can we study them? And this was something that I started here, and then I kept interacting with the people I worked here, and we actually eventually were able to produce some scientific results in a few years' time from 2018.
So how did you get there? Do you have a link to your
Uh,
IISR?
No, not really. I just found this a professor there who worked like on some interesting topics. He seemed like a very interesting guy. I just wrote to him that, see, I really like that this work that you've been doing. Would it be possible to maybe come for a month or two just to learn from you and see if I can work on something? And at that time, actually, ISRO had this competition where they were like, we have this imagine that we are planning to send say a rover or a lander mission to one of the moons of Jupiter. Then what would be the scientific proposal? Like, what would be the scientific goals it would pursue? And it asked, like, basically all undergrad students across India can form teams to build a scientific proposal and go for it. And I was like basically leading one of the teams from our institute, and we went till the finals, but the finals was like uh, basically in it was coinciding with our final exams, and we didn't go for the final competition instead. But when I talked about this with the professor, because he wanted to know what background do I have in terms of in astronomy, he found our approach quite interesting. Basically, the way we developed the mission proposal, and he was like, you know what, you can just come to Santa Barbara, and then we'll figure out what you can work on. And once I was there, he set up a meeting with one of the postdoctoral fellows there, and we came up with this idea that, okay, we can work on something like this. And it took a while, definitely. I was still 2 years into my undergrad, and that's not enough information to start doing actual research. And I actually published the research in once I was already in my PhD, like in my first year of PhD. But yeah, I would say it was more of a matter of luck that I approached someone who was actually interested to entertain me.
Well, it's not a matter of luck. I sometimes tell people that if you are stuck, then the way out is to not look at the institution, but to find a professor.
Indeed. Yeah.
Really.
Yeah.
Like, because if you talk to the institution, you sometimes don't get any response. But if
Hmm.
you find a like-minded professor, sometimes you get a response. Not always, but it's another
Yeah. Yeah.
way.
Yeah,
Okay,
I mean, at this point, I was I was talking to a couple of professors, and he seemed to be willing to take the jump. So
okay,
I guess that worked out.
okay, fine. Let's continue.
Yeah. In the next year, actually, that's when I applied for a formal program. So the German Academic Exchange, the DAAD program, has a internship program where they fund students to come and spend 3 months in Germany in a university. So they call it the working internship for science and engineering. And I was able to talk to a professor at the University of Heidelberg in Germany, and we came up with a project plan that he felt was something I could approach based on my past experiences. And I was able to get the funding. So in 2019, I visited Heidelberg, and I worked with, again, with galaxies, looking at these really big black holes, which we not so creatively name supermassive black holes in their centers, and how do they behave. So I was going with the theme that I've worked with galaxies before, let's continue doing that.
Okay,
And it was definitely interesting. And it was here that I got to know about the PhD programs in Germany. And then for my master's thesis, actually, I was like, okay, I've worked with galaxies. I've just done a lot of calculations and everything. Now, what about if we actually use observational data? What if we actually use data that is collected from telescopes? So I talked to people at the Center for Astrophysics at Harvard and Smithsonian, and I was supposed to visit them for 6 months. Like, we have a 1 year for a thesis, so I was thinking of spending half of the time there and half of my time at my home institution to basically work on X-rays coming from stars, not from our own star, but from nearby stars, and kind of study how they behave and interact with the planets using that. But unfortunately, this was the period when the pandemic struck. And instead of being able to visit them, I was working remotely, which meant that I was working according to the US time so that we could actually talk to people.
yeah,
And in India, that would be at night, but
yeah,
we somehow made it work.
yeah.
And that those were all really enriching. And then eventually I applied for a PhD in astronomy, and now I am here at the Max Planck Institute for Astrophysics, where I'm building and improving these really large computational simulations about what we would actually see in the sky if we could look for radio signals from the very early universe. And then we change the parameters of these simulations a little bit so that we get different kind of pictures of the universe. And then we use that as a training set for a machine learning algorithm, which would then give us an idea, okay, this machine learning algorithm, if I send it at my data, it would be able to find similar signals from the data. So that's basically the idea that we have, and we have been pursuing that. And
What
just
is early universe?
yeah, I just go into that with my PhD research. So that's basically a very good question, and that's what this slide answers.
Okay,
So basically, in the universe, we have this picture that, okay, there was the Big Bang, then eventually this universe was expanding. We formed the first atoms of hydrogen and everything. Then for a while, nothing really happened. Just the universe was growing in size. There were atoms flying around, uh, and that's pretty much it. But eventually, we know, because if we look at things with our telescope now, at present day, that stars, galaxies, and everything form. So at some point, it would have been the case that the first stars formed, the first galaxies formed. And what it does is that whenever they form, because they're emitting light, the light would basically, if it hits any atom, it would transfer some energy, knocking out electrons from it. And if it knocks out an electron from a very simple atom like hydrogen, which has only one electron, it would lose its electron. And that's what we see in the present day, that around the galaxies, there is not really any atoms left. It's just electrons and protons separated. But in the early universe, there must be a period where there were some places where there were just a few stars forming, a few galaxies forming, and some places where there were just tons of just atoms floating around. And we are interested, that's what we call the early universe. in terms of the community, we call it cosmic dawn, which is the first stars and galaxies formed, and then the epoch of reionization. The name is a bit complicated. We would not go into it, but that's basically the period. So what the with the James Webb Telescope, what we usually see is these galaxies, but we are not really interested in them. What we are interested in is when these galaxies were forming, what happened to the atoms in the space here. Essentially, everything that's dark seems dark because the James Webb looks at uh, photons coming from a very specific wavelength, which is now in the infrared regime. But what we are interested in is actually in the radio regime. So what is looking black here would look really bright in terms of the radio signals. So the radio telescopes would actually be able to see this. And this is where we have basically atoms of hydrogen, and we believe that they can emit a radio signal which is strong enough to detect now. But it's really difficult because you have entire galaxies emitting so much light. So just something so dim that it looks dark, the emitting light would be difficult to find. But we do try. We run simulations, we make different possibilities so that we could generate a large range of simulations. We train a machine learning algorithm, and we are looking for that signal in the data. So far, nobody has been successful, but it looks like that the methods that we are developing could be one of the best possible techniques out there to actually eventually find the signal.
Okay.
Yeah.
Okay, it's very good.
Indeed, it's one of the most difficult tasks, but it's still a very interesting problem to approach.
No, it's a problem that is, what should I say? Clearly, you have clearly defined the issue.
Indeed.
Right? You have defined the issue, and nobody has an equation yet to explain it. So you are just hunting in the dark for it.
Indeed,
You
pretty
are
much.
hunting, and you have a great telescope to get the data, but the data, I guess the radio signals come in huge quantities. Somehow you
Yes.
have to sort them out, and that's why you need the algorithm, because it's too
Yes,
hard for
because
everybody.
even a lot of times, like if the what happens is, for example, the Earth has an ionosphere because like it has ionized atoms and everything in its atmosphere. That releases its radio signal. We as humans, we release a lot of radio signals with everything that we own, and so even those little tiny things can make things complicated. So we have to extract everything out and then see what we find. So
Yeah,
that's why it requires a bit of an effort, and that's why nobody has been able to do it yet. But
right.
maybe eventually we will.
Yeah. Okay. So I understand that there's so much data and that
Yeah.
you really aren't really able to look at it. Hopefully,
Mhm.
ML can look for it, and then you can have human intervention to check it.
Yes.
Right
Yeah.
now, at least it needs to give you maybe 10 or 7, whatever, probable probable outcomes or results, and then you can look at it. Okay. It's very
Yes.
interesting, I must say, in terms
Yeah.
of you are into pure physics, and then this could be sort of you're saying, okay, wow, I am really looking at some data and I'm trying to understand what
Yeah.
happened. What I mean, you're suppose let me ask even a more uh, what should I say, forward-looking question, which is
Yeah.
another way of saying stupid.
Oh, no, no.
Suppose you found the signal in the data.
Yeah.
What would you do with it?
The first thing would be to see that. So we use one set of telescopes. We use the low frequency array LOFAR telescopes in Europe. We would want telescopes that are run by American and Australian groups to also kind of confirm this, because you can't really just go and make the claim. You really need to be sure that other people are finding it. And once you do, what you basically are able to constrain is how fast did the first galaxies and stars form. And what that kind of gives you an information of is basically the more fundamental physics for like equations, like how exactly did matter come together and everything. So it
Mhm,
governs equations of gravity and everything. So
mhm.
that kind of gives you a better idea of how exactly does physics operate at more extreme scales, and uh, what can influence it. And it basically gives you just a better picture of physics that you can then utilize, because a lot of times what we have right now is that we know that physics probably could change at scales which are, say, when there's an extreme environment. For example, the very early universe was an extreme environment. Everything was smaller, closer together, and everything. The first stars forming is something sudden. It is an interesting environment, but we don't really have a way to test these things. So this kind of gives, because these are just not something we can replicate on Earth. But once we can get a handle of how does physics operate, you could then find ways to uh, utilize that understanding in order to go into other aspects which could actually be usable. In the sense, for example, we do not understand how to do, say, for example, nuclear fusion, like in a way that would be actually generating energy. This is
Yeah.
because we don't know how exactly did the first stars actually come together
Yeah.
to then start something that could sustain. Uh, so having a picture of how exactly that happen in nature could give us an idea of how to can we replicate it in a way that where we are actually generating energy more than what we pump in to set up the system.
Mhm.
So it kind of is a way to basically have the basics right, so that then you can do a bunch of other things.
Okay. All right. Do you have any more things, slides at all?
Just a few about the like about how people can get into
Okay,
astronomy.
so let's go ahead.
Yeah. So in India, like usually, like this is not something related to just India. I would say that usually a bachelor's in physics is preferred. In India, this would be in, say, national level colleges, which usually have this integrated system of giving a bachelor's and master's degree together in a variety of universities. But there are also state and private colleges which have like 3 or 4 years bachelor's degree, after which one would typically do a master's degree. But of course, there is also the option now that one could do a BTech in an engineering degree, preferably in computer science, mechanical engineering, electrical engineering, IT, something like that, and then switch to physics for a master's. This is more difficult and ideally not the best option. But of course, if somebody, say, changes their mind, like they did a engineering degree but now want to get into astronomy, maybe they can do this. And then, of course, after a master's, they can pretty much apply for a PhD anywhere. In programs in the US, Canada, Australia, and now even in India, you could also directly go for a PhD after a 4 years bachelor's, which is nice. But there is a catch, of course. In India, while they focus more on competitive exams and interviews, in other countries, usually what I saw when I was applying, because I applied to a bunch of places, was that the focus is more on the research experience you have built so far. And they want practical experience to be showcased. And then that needs to showcase in terms of your written application, letters of recommendation, and maybe they would also have interviews where they say that, okay, so what have you worked on? What did you learn from that? And things like that. And what after a PhD is like, usually people would say that, okay, you do a PhD, you do a postdoc, you go tenure track, tenure, that's it. But in reality, what we see in as astrophysics is that a lot of people actually leave the field because of a variety of reasons. The field itself is quite competitive, and there are not as many positions as there are PhDs graduating. But there's also the fact that there are a lot of non-research and even industrial research jobs out there which require the skill sets that one has. So even at each step, while the number of people leaving reduces, there is still a decent number. And there are actually a few people who are tenured professors who I know have also quit research to set up their own companies, because they went really into uh, developing these data science and data analytics setups, which were really in demand for like consultancy services, finance, banking, and things like that. And while mostly these people are employed in universities, there are also research institutes, observatories, and even planetariums and museums that employ people just without giving really differential ranking. It's just they call them a scientist or, say, a chief scientist, and that's about it. And but one could say that, okay, all that is the formal thing. What can a student just do by themselves? And that is actually a good question. because there is actually a lot of resources out there, starting from, say, textbooks that undergrads could follow to popular science books. And here I took a moment to highlight books which are less known so that people don't just go after the most popular books out there. And the key things why I show these books specifically is that, firstly, for the first one, the free PDF is available online because the authors want people to read their book, and so that they can have a flavor for what astronomy teaching looks like in college. And the second one is a cheap Indian textbook that you could easily find everywhere in India. And among the popular science book, First Light is by Dr. Emma Chapman, and she works on topics related to my own work. And the other books, Big Bang by Simon Singh and The Biggest Ideas in the Universe by Sean Carroll, are really nice books to get into, even if you do not have a scientific background. There are also quite a few YouTube channels which have been doing excellent work. Like Dr. Becky, she talks about what it's like to be an astrophysicist by uploading videos just from what she's been working on and her workspace. Then there's Cool Worlds, which is led by a professor in Columbia University who talks about topics that his group has been doing research projects on. Then there are more formalized videos by like PBS Spacetime, SciTime, which also employ scientists and astrophysicists to explain things. And there is an initiative in Germany called Kurzgesagt, which tries to explain scientific concepts or even really wacky out there kind of research in simplified formats with like videos which are accessible to all. There have also been efforts by people within the community to make it reachable for all. And there is this amazing guide called Astronomy as a Field, a guide for aspiring astrophysicists, which is again available as a free PDF on archive.org. And there is a compilation of free resources of learning how do astrophysicists use programming, how do they use statistics, what are the physics concepts that go in, what are the resources for all of this? And that is all listed in this website, astroteaching.github.io. And that is an amazing thing that so much information is out there for free. And I would just zoom past this because we've already talked about this, is that observers usually just use telescopes and then do a bunch of data reduction and analytics. So there's a lot of programming involved, while theorists build simulations on supercomputers, which end up looking something like this, which is basically a map of density of fields, where wherever there is an interconnection, that's where a galaxy could form. And both of these involve a lot of programming. So this is the background is from the James Webb Space Telescope. It's called the Carina Nebula. And here is something quite cool. The M104 is actually a photo of a galaxy that I think Hubble Space Telescope saw. And the other 5 are actually from simulations which just happen to reproduce something similar. It does not look the same, definitely. We still are not there yet to make perfect simulations, but we are able to actually get somewhere close to it, which is quite interesting. But all of this still involves a lot of programming, so we need to really have an understanding that an astronomer or astrophysicist is no more someone who just looks at things in the sky. They actually spend a lot of times hunkered down on working through code and trying to understand how to represent their data best. And just to conclude, astrophysics, while it sometimes feels like what exactly is the importance of this field, it's not really contributing directly to human betterment. But in a way, it does. It is one of the oldest sciences. So while looking at cave paintings, it was found that there are some cave paintings of people laying down and looking at the sky, trying to make sense of it. And as time progresses, that has just advanced. We have just had better tools to look at the sky, coming to Edwin Hubble looking with telescopes, and now we have computers who operate telescopes directly. But the history of astrophysics goes back to the history of humanity, and it basically provides a framework for us to run experiments that are never possible on Earth. Some things can happen out there in the universe that we simply cannot replicate on Earth. So with astrophysics, we can learn about the sciences in a much deeper and fundamental level that nothing else can teach. And something that has been quite interesting is that the technologies based on techniques that actually were developed in the field just to answer questions of astrophysics turned out to be actually useful. For example, the fast Fourier transform method was developed, which turned out to be helpful for the actually having Wi-Fi spread across a room. Otherwise, it was found that Wi-Fi signals died down too early. And medical scans like CAT scans, PET scans, take from aperture synthesis, which was actually developed by radio telescopes for interferometer measurements, which again, astronomers didn't know what they were developing. They just wanted something that works for their systems. And then they realized that, oh, wait, we could use this in different concepts as well.
Hmm.
And in the end, a lot of people are attracted by the fundamental curiosities that astronomy actually tries to answer. It's easy to bring people to science using astronomy as a picture, and then they can see, okay, what exactly do they find genuinely interesting? So as a first introduction to science, astronomy has always played a crucial role. And thus it's a beautiful field to be in.
Okay. Could you tell us a little bit more about this Wi-Fi thanks to FFT? I have no idea what is FFT.
Yeah, so basically, what it was found was that initially Wi-Fi signals would die down really easily after a few, say, reflections. So you could not really have them spread across too much. So what fast Fourier transform does is that it forms a very, like, it transforms the signal. Instead of just sending all frequencies together, you kind of break down the signal into how strong is each signal. So you quantify at this frequency, what is the strength of the signal? That's the information you store. And if you send that information around, that could actually, like, you know that, okay, if everything dies down, you would still have that, okay, this frequency is stronger than the other frequency. Even if this reduces, they would reduce equally, so that information still stays. So that earlier, this is basically what Fourier transform does, but Fourier transform was expensive to calculate. The fast Fourier transform is basically an approximation that astronomers built to run this basically very fast.
Okay.
And that has helped. And aperture synthesis is somewhat more complicated. Basically, it says that if we look at things from two different observing units, then how do we stitch them together to form a single picture?
Yeah.
So it kind of
Yeah.
cat and pet scans where you have multiple things looking at a human body
Yeah.
to
So,
get a 3D picture
I
out
mean,
of it.
these are very important of
Indeed.
Wi-Fi and CAT and PET scans. They are
Indeed.
quite important, and obviously somebody had to have a theory for it, otherwise we couldn't get it, you know. That's clear. So that's actually medical imaging now,
Yeah.
CAT scan and PET scans. And I mean, I'm old enough to remember when CAT scans first came into being and PET
Yeah.
scans came into being. And it was a huge breakthrough because before that, you only had X-rays, right? And then
Yeah.
X-rays
So the CAT
really,
scans were actually developed, I think, I don't remember, but I think in Australia or somewhere. But basically, it was an astronomer who quit the field and then become a medical physicist.
yeah,
And they were the ones who registered the patent for CAT scans.
yeah. But you know, it was a huge breakthrough because
Indeed.
in half of, I mean, as you get older, you get more familiar with medical things, and
Yeah.
young people don't have to bother about them. But what I'm saying is that actually the doctors know only because they can see inside you.
Mhm.
Because if they can't see inside you, they really don't know. Okay.
Yeah.
They really don't know what's going on because all the other data and all are actually no substitute for the picture. The
Yeah,
picture,
that's true.
the picture rules, you know, the picture rules. It just shows what's going on inside you. And CAT scan and PET scans are really very, very now common. And PET scan is still a little more complicated, but CAT scans are very cheap and they
Yeah.
do that. But you really get to see the picture, which X-rays won't show. Okay, so it's
Yeah.
really a major contribution apart from the fundamental curiosity. Okay, all right, let's get on with it.
Yeah, that's pretty much it. After this, I just wanted to quickly flash my socials. If anyone who wants to reach out to me for more questions can always
Hmm.
just drop me a message here. That's
Okay,
about it. That's pretty much it from my side.
okay. So can we get out of this share screen?
Yeah.
Yeah. Okay. All right. So, uh, to a person, to me, uh, one of the amazing things or amazing persons is Galileo,
Indeed, yeah.
because he said, and yet it moves.
Yes. That 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 is indeed like that's why I would say that he's actually very well regarded in the community because he valued the what he saw, what he calculated, and it made sense to him. And he was like, okay, this is the science. We can see this, we can prove this. And he went
And
against basically everyone and everything in
yes,
order to justify the fundamental understanding that he was able to derive. And
yes,
that's amazing.
yeah. Under when the church told him no, uh, the earth stands still. Under his breath, he said, and yet it moves.
Yes,
So that to me stands out like the triumph of science. Okay, that look, guys,
indeed.
you don't know a damn thing. I know what's
Yeah,
going on here, and I'm telling you. And of course, the whole world changed after that.
yes,
Whole world changed, and those were very, very elementary days. I take it. Nobody had any instrument or anything, and
yes.
probably they
Yeah,
also,
it is actually amazing how with very rudimentary
yeah,
stuff, people were able to do a lot of science.
yeah.
Even without telescopes, there were people who were just looking at the sky with just their eyes for really long or on several nights and were able to figure out a lot of details about how planets move, how maybe the Earth is moving just based on what they were seeing with their eyes.
But I want to say that I have read. These days I don't remember everything I read, but I know that there have been amateur astronomers
Mhm.
who are not theoretical people but practical people, as you
Mhm.
said, the observers, and they
Yeah.
have found things which were sort of path breaking. Is this true, or my memory is faulty?
Yes, sometimes you can get lucky. The thing is, a lot of times, like because the sky is huge and you can only point your telescopes on certain regions of the sky, and this actually boils down to really small regions in the sense that uh, a lot of the telescopes which are really big and everything still gather data from, say, if you put a coin at arm's length, whatever is the size, that's the amount of the sky they see. So if somebody happens to point their own, say, binoculars or their own private telescope at some part of the sky, it is possible that they find something. And it has happened. Like people have found supernovae, people have found comets, asteroids, a lot of these different celestial objects just by chance. And a few of them actually they would spend time looking at it if they could so that they gather more data and they were able to even identify what exactly were they seeing instead of just being like, okay, I saw a bright light. They're able to identify, and that is quite amazing. Like basically anyone who can look up at the sky with the right tools can really find something interesting out there, which is really nice.
Okay, so you showed me a chart with X% of, let us call it attrition or depreciation or attrition.
Mhm.
So, where is your path if you know it?
I mean, honestly, right now I enjoy the science too much to leave it. And there is a lot of interesting things that I would like to do. So I'm at the moment, like I would be applying for jobs in this coming, say, next few months. And I am still looking to apply to jobs in research. So I would be applying for these postdoctoral research fellowships and things like that so that I can still continue doing astrophysics because there's still so much to do and still a lot of excitement
And
that
where are they located, these postdocs?
and I mean everywhere around the world. It just matters to what exactly is the kind of science I would want to do. So for example, if I want to go deeper into supercomputing and the simulation development, then the United States still has a lot of amazing facilities for that. In Europe there is a mix of both observations and theory. While places like Australia, South Africa, they actually have massive radio telescopes coming up. So, for example, Australia has this called the Square Kilometer Array, where they put these small radio dishes up to 1 square kilometer area, so that combined together you can really get like make them act like a big telescope.
Okay.
So these things are coming up in places. So it basically depends on where one wants to go and what one wants to do.
Okay, fine. All right. You didn't mention China or India. So are
Yeah.
they?
China is definitely doing well. In
Uh,
India, there are places, but the thing is, again, you need a certain amount of funding in order to be able to do internationally competitive science, and that is like very competitive in India right now, like to get that kind of funding. So
okay.
there are positions, there are people doing really good work. It's just that to get into that, it
Okay.
would
Yeah, I
probably require
understand.
more experience outside before I can compete with that kind of a crowd.
Okay. All right, fine. I'm just curious. I'm actually more curious about China. Are they
Yeah.
spending tons of money on this
Yeah,
or?
China is doing a lot. It's just like they are pushing really hard. They have probably the best. They have facilities coming up which compete with everyone in terms of everything. So they are really like they're almost there. It's just that they have this issue of language in the terms that often they're not able to you won't see them coming into international conferences and presenting because sometimes they have an issue with presenting things in English or something, but they're still producing a lot of research which is top notch. So uh, their their writing is fine, and the scientists from there who actually are coming, they're doing really good research. So it's just they're getting there. They might very soon cross the US as well.
Okay. Anything else you want to tell us?
No, I guess that's been a really nice conversation, and thank you for this opportunity.
Okay. All right. Any tips for young people in India?
I would just say that, yeah, like if you find things interesting, try to take out some time to pursue it beyond learn it for the sake of learning instead of for like, okay, I want to score high in marks in an exam or I want to go into this college, because things will even out in the end, like as long as you're kind of interested in what you're actually doing.
But somebody might say, listen, it narrows my options very fast. But what you are saying is it doesn't, because you actually can get jobs outside the field in practical
Indeed, indeed.
stuff.
Like,
So
yeah, so
tell us a little bit about some of the jobs that you know some people have got.
yeah. So basically, because astronomers and astrophysicists do so much programming and statistics, their key skill areas are basically programming, software development, data science, data analytics, uh, big data analytics, and statistics. So they are mostly going into, like nowadays, they are going into consultancies like, say, EY, Deloitte, and these for uh, basically wherever there is uh, people coming with lots of data and they want to make sense of it, or they're going to banking or finance, where for example the finance side has like the stock market, so they want people who are involved in quant research. And astronomers, it is their bread and butter. They look at past results, they try to predict future results, which is what the stock market wants. So that is also a common area. And in banking, of course, you want to know and build models like, okay, the likelihood of defaulting and things like that. Beyond that, there is also the tech industry, which really it is a it is a bit murky, but they really want to use user data to analyze user behavior in the future. For example, something as basic as, say, an app which is selling stuff, say Amazon. They want to study, if a user buys these 5 things, what are the things that should show up in a search result so that they're likely to buy again. So these are relations which basically say how related are things, which is a very basic question that is essentially a programming or a statistics question.
Okay.
And
All right.
people, astronomers, go into these kind of roles
Yeah,
of
yeah,
data
I
science.
understand. I mean, basically, it means that you take the underlying skills rather than
Indeed.
subject matter.
Yes.
And you have the underlying skills and the proof that you are a very clever person, you are a very clever thinker, and you can think
And you are
about.
able to work with like where you do not know what the result could be. You do not have a framework, but you
Okay,
build your own framework. You build your own algorithm to
all
approach a
right.
problem.
Okay, thank you so much, Anshuman. It's very illuminating. Let me put it. The light has come. So let's end it here. And
Yeah.
I'll be back with another young person or an expert or a young expert soon. Bye till then. Bye, everybody.